This is a non-calculator FRQ from 2015. We're going to focus on the non-calc. It's really typical for you to be given a table of data and then have to manipulate. So this is a situation where we're dealing with a jogger along a path and we're looking at a velocity, right? So the velocity is given. It's important to understand what you're given. It also states that you're dealing with a differentiable function, so you don't have to assume that. They state that. And then it makes sure that you pay attention to your units. Your units are in meters per minute, so you're going to be expected to be able to execute which unit you are dealing with in each of these questions. All right. Part A is very specific. Use the data in the table to estimate the value of v prime of 16. Okay, v prime indicates that I'm looking for a rate of change. So v prime is going to be acceleration. That should help me a little bit with my unit. But remember, it's got to be an estimation. So v prime of 16 is looking at what's happening around t equals 16. So even if t equals 16 was given to me on the table, I'd have to use the points around 16 in order to create a line. So we're going to say v prime of 16 is going to be approximately, because we're not executing the exact value, we're just trying to get an approximation. So it should be v of 20 minus v of 12 over 20 minus 12. That is what you call your difference quotient. You have to show that piece. Now I do have values for this, right? So v of 20 is 240 minus 200 over 20 minus 12. Be really careful. It's typical for you guys to mix this up, for you to flip this, right? So make sure that you've got your y values on top and your t values in this case, okay, on the bottom. And now a little bit of manipulation, and I'm going to make sure I get my unit on there. So I've got 40 over 8, very easy division. So I know I'm dealing with my answer is 5. The question is, what is my unit? And my unit does matter. So it is going to be meters per minute per minute. That is an acceleration. So it's going to be meters per minute squared. That is what we are looking for. All right. Let's go ahead and look at B. Let me move this up just a little bit so we can move through this. Using correct units, explain the meaning of the definite integral. I'm hoping that this jumps out to you as the absolute value of velocity. And whenever you integrate velocity, you get displacement. But if you integrate the absolute value of velocity, you're looking at a total distance traveled. Everything was positive, right? So you're looking at the distance traveled. I'm going to use that as my explanation. It does ask us to approximate the value using a right Riemann sum with 4 subintervals indicated in the table. So let's explain the meaning. We've got this piece. In the context of the problem, we can't just say total distance, right? So we're going to say indicates the total distance that Joanna traveled, because that is the distance that she jogged, right? So the total distance that Joanna jogged, and it does want me to include units. So in meters, and it's really important that you include the time. So anytime they're asking you to explain something, you need to include the time, the what, and the unit. So we've included the unit, so we've jogged in meters from t equals 0, right, to t equals 40. If you want to write that in an interval, you could have easily written it like that. But you do have to indicate a time. So that's what we're looking for. Now we're going to use a right Riemann sum to estimate that. So right Riemann sum, I want to deal with 4 subintervals. So there are my 4. Those intervals are not universal widths, so I'm going to have to pay careful attention to that. So the first one is 12, the second one is 8, the third one is 4, the fourth one is 16. Now I'm dealing with an absolute value of velocity. The absolute value of velocity means I am not worried about that negative sign right there. So I'm just looking at the total distance traveled. So the fact that she slowed down or started going in a different direction means nothing to me. Okay, it does not matter to me at all. That's a different direction piece. That's not a slow down piece, but it does not mean anything to me in this case. All right, so we're going to say that the integral from 0 to 40 of the absolute value of velocity is approximated. Now remember, that's the notation that I use. You don't have to have that in order to get this correct, but I use the right Riemann sum piece. And now I'm going to start with the width. So the width of the first one is 12, and then the height of that rectangle, right Riemann sum. So I'm going 200, 240, 220, and 150. It's got to be on that right side. So 12 times 200 plus, and then the next width is going to be 8. So I've got 8, and then that height is 240 plus, and then I've got 4, and then that height is going to be 220, and I'm not worried about the negative. It just means she went the other way, right? And then plus, that distance is going to be 16, and then I've got 150. Now, remember, this is non-calculator, so that might be a little overwhelming to you at first. Your AP exam is going to allow you to use the 4-function calculator, so you can do that. It's also not going to require you to simplify. So weirdly so, you could easily stop here. I wouldn't do that for me because I can't end there, but you could, as long as you attach a unit to that. The 12 times 200 isn't too bad, so you get 2400 there. And then the 8 times 240 might bother you, but the 8 times 240 is 1920. Again, you would have a 4-function calculator available to you for the 2020 exam. Then this one is going to be 880. And then 16 times 150, pretty easy. That's 300 times 8, so that's 2400. So a little simplification there. The 880 and the 1920 actually add up pretty nicely. You get 2800. So 2400 plus 2400 plus 2800 is going to be 7,600 meters. Now remember, that is a total distance. So this situation where she turned around and went the other direction does not matter to me. All right, so that is Joanna jogging on that one. Now we've got a little bit of an addition. This is pretty typical on an FRQ. They're going to say that Bob is now riding a bicycle along the same path. So now it says that Bob's velocity is modeled by an equation. So we're going from looking at the table to now looking at the equation. And T is, of course, measured in meters per minute, so I have not changed my unit in any way. And it wants us to find Bob's acceleration at T equals 5. Now, this is not an approximation. I am given a function, so I'm going to be able to do this exactly. So if I'm going to look for the acceleration, that means I'm going to have to take the derivative, because acceleration is the rate of change of velocity. So I'm going to have 3t squared minus 12t. That's going to represent Bob's acceleration. So all I'm looking for here is b prime of 5. So 3 times 5 squared minus 12 times 5. That simplifies pretty easily. You get 75 minus 60. So let's go ahead and attach the correct unit to that. You're going to have 15 meters per minute squared, right? Acceleration. So acceleration requires that meters per minute piece. All right, and then the last part is part D. And part D says based on the model, so this is the model that it's referring to, is that B of T. From part C, find Bob's average velocity during this interval. Okay, we talked about this. We have an average rate of change, and we also have an average value. We have two different formulas that we use in calculus. So the question is, which formula am I going to use? What am I going to diagnose this as? Well, it's important for us to recognize that that is the equation for velocity. So if I am looking for the average of that equation, I am looking for the average value. I don't want the rate of change of velocity. That's going to give me acceleration. I want the average velocity, so I'm going to use average value. So average velocity is going to be the 1 over b minus a, so 10 minus 0, times the integral from 0 to 10 of t cubed minus 6t squared plus 300 dt. Now this is going to take some execution here. So I've still got the 1/10 on the outside. I do know how to integrate this. This is just a regular algebra situation. So I'm going to do 1/4 t to the 4th minus, add 1, right? So you're adding 1, you get t cubed. You divide by 3, you get 2. And then make sure you get your 300t there. And this is being evaluated from 0 to 10. Now that 0 sure is nice. That helps us out a lot. So when we do our f of b minus f of a, I'm going to put the t in, or the 10 in, excuse me. I'm going to put the 10 in everywhere I see a t, but then that 0 is going to mean, so there's my first, this is my, everything's going to turn into 0. Now that doesn't always happen. Please be careful with your zeros, but in this case, multiplying by 0 is obviously giving me 0 for everything. I don't have a constant, but it's not a natural log, it's not an e, so plugging in a 0 eliminates all the pieces. Again, if we use the correct unit, we could stop there. You could say equals 1/10 and just plug in all of these pieces and just leave it right there, and then just attach your unit, right? Well, this is measured in velocity, so it's meters per minute, because it's an average velocity. That's fine on the AP exam. You do have a calculator available to you in terms of for function, so you should be able to execute this pretty easily. 10 to the 4th is going to be 10,000. A fourth of that is going to be 2,500. And then you've got, oh, that should be minus, I'm sorry. Got to be careful with that. Minus, and then this is going to be 2,000, and then plus 3,000. So it looks like you've got 500 plus 3,000, so 1/10 times 3,500, which of course is 350. So 350 meters per minute. You do not have to waste your time on the AP exam simplifying it, but if you have access to a calculator, that's not going to be tricky for you. Now, knowing what the question is asking and how to diagnose is always going to be key, but knowing that for this, you always have to have units attached is also something else I need you to consider. So make sure that you're always looking at units and then diagnosing, especially with average value versus average rate of change.